Last topic for this lesson is evaluating clustering. Being able to perform clustering in different ways is only useful if you know how to evaluate different clustering methods and compare them in an objective way. Subjective methods, such as visual inspection, can always be used, but the silhouette score is a powerful objective method that can be used with data that is more difficult to visualize. We will learn more about this in the next section. The silhouette score is a formal measure of how well a clustering fits the data. For each point, the silhouette score is calculated as follows, and here xi is a data point, axi is the average distance between the data point and all other data points in the same cluster, and bxi is the average distance between data point xi and the next nearest cluster. Let's go ahead and do an exercise to understand this better. Please keep watching. Calculating silhouette score to pick the best k for k-means and comparing to the mean shift algorithm. In this exercise, we will perform k-means clustering using different numbers of clusters and use the silhouette score to determine the best number of clusters to use. We will also compare the scores obtained using the k-means and mean shift algorithms. We imported pandas and read the data in forcalls.csv. Now in this step, we standardize the data in each column by looping through each column and stored the result in new columns named with z_ prefix. To begin the clustering, we need to import cluster and matrix from sklearn and also import matplotlib. We are going to start with k-means clustering. Now we created a list of numbers and we used for k 2 to 10 and stored it in a variable called krange. We created an empty list called average silhouettes, which we used to store the silhouette scores. We looped through the values in krange and performed k-means clustering for each value of k and used the silhouette score function from matrix to calculate the silhouette score. We appended the silhouette score to average silhouettes. Now finally, we are going to plot the result by plotting krange against average silhouettes. Now from this plot, you can infer that K5 has the best silhouette score. Now in this step, we performed k-means clustering with the best k we found and then printed its silhouette score. And next, we performed mean shift clustering with a quantile of 0.1 and printed the silhouette score of the resulting clustering. Now, we should note that the mean shift silhouette score is very close to the k-means score using the best value of k. This means both provide an equally good fit for the dataset. I hope this exercise gave you a good understanding of silhouette score and how to use it. A very common concern in machine learning is the problem of overfitting. Overfitting is when a machine learning model fits so well to the data that was used to create it that it doesn't generalize to new data anymore. Clustering models and other machine learning models can overfit data, meaning they seem to fit data they were created with very well, but do not generalize to new data well. To overcome this, best practice is to remove some data which will exclusively be used for evaluating models, with the rest being used to create the model. The data used to create the model is called the training set, and the data for evaluating the model is called test set. Now let's go ahead and do an exercise to understand this better. Using a training and test split to evaluate clustering performance. In this exercise, we will separate the data from forcalls.csv into a training and test set. Then we will use the training set to fit our clustering algorithms and then evaluate them on the test set. As a first step, we imported pandas and read in the data from for_calls.csv. And then we standardized the data in each column and saved the results in new columns named with a z_ prefix. Now we are importing model selection from sklearn to use the train test split function to split the data into training and test sets. We're storing the resulting data frames in xtrain and xtest. Now let's go ahead and inspect the data using head function xtrain. The first 5 instances of the data, training data, will appear as this one. Now check the test data. Everything looks good. Now at this step, I'd like to check the lengths of the 2 sets to see how the train test split function works. You will observe that the length of training set is 750 and the length of the test set is 250. By default, train test split function produces splits where the test data is 25% of the data and the training is 75%. This can be altered with the test size parameter. Now, we performed mean shift clustering on the data, imported cluster and metrics from sklearn. We used a quantile of 0.1 to estimate the bandwidth on the training data, created a mean shift model, MS, with the resulting bandwidth, and used the fit function of the mean shift model to fit on the training data. Please note that we have been using fit predict previously, but here we are just using fit. We can call the fit and predict methods separately to fit using one set of the data and then predict with different data. Now we use the predict method of the mean shift model to produce cluster labels for the test data and stored the labels in an MS labels variable. We calculated the silhouette score for the test set using the silhouette score function on these labels. We stored the values in an MS silhouette variable and printed them out. Now we performed k-means clustering with 5 clusters, again using the training set to fit and the testing set to calculate the silhouette score. We printed the score for the clustering as you see on the screen. Now note that the silhouette scores of the 2 methods should be very close. This just means they are performing pretty similarly. So there is no reason based on performance to strongly prefer one or the other one. Now we performed mean shift clustering again, but this time with quantile set to 0.01, again fit on the training data and calculated the silhouette score on the test data. You should get the mean shift silhouette score as you see on the screen, and this much lower silhouette score shows that the algorithm performs much better with a higher value for the quantile. So I hope this exercise helped you understand how to separate data into training and test sets.